Welcome back. In the last lecture we have introduced conditional logic C, and then this C should take care of ceteris paribus clauses as well. The idea here is that when you are analyzing a conditional sentence A implies B, it is understood in the sense that A together with ceteris paribus clauses leads to a conclusion, another conclusion B, where B is considered to be consequent and A is considered to be antecedent together with the ceteris paribus clauses. So now the idea here is that the main idea here is that in all the antecedent permissible worlds, whether the conclusion is true or not is the one which we are going to see. So to begin with, we are trying to talk about the accessibility relation, particularly in the case of conditional logic is quite different from the one which we have used in the modal logic. Here accessibility relation is with respect to the antecedent of your conditional. There are two things which we have seen in the last class, that is FAW. FAW is considered to be a kind of selection kind of function which picks up the nearest possible world with respect to the antecedent. The nearest possible world, usually it will be non-empty. So now if we keep on imposing some kind of restrictions on the accessibility relation, then we will be moving away from C, and of course we will be talking about C plus in that context. Just like in the case of normal propositional modal logic, we started with K and we started imposing more constraints on the accessibility relation. For example, if R is considered to be reflexive, if two worlds are related in such a way that X is accessible to itself, then it holds in reflexive frames. There are some formulas which holds in reflexive frames. In the same way, if you invoke symmetric property, we have symmetric frames, etc. Just like that, even in the case of conditional logics, we begin with the minimal conditional logical system C, and then we will be imposing some restrictions on the accessibility relation RA. Then we will move on to C plus, and then the C and C plus has clear cut semantic tableaux method for showing the validity of a given formula. But conditionals are not easy to analyze with the help of just C and C plus. We require some more semantics, like more and more constraints needs to be added to the accessibility relation, and that results in C1, C2 and S. Unfortunately, S, C1, C2 has no, as of now there is no appropriate semantic tableaux method for showing the validity of a given formula, but although there are efforts to show that C1 and C2 has some kind of semantic tableaux methods which are possible, but as of now we do not have appropriate semantic tableaux method for such kind of systems. So to begin with, in C, the main condition is this thing. FAW is like this. Suppose if you have a conditional A implies B, so this means A plus CG, and ceteris paribus clauses leading to B. So FAW means this one. This is the word that you began with, W, and then FAW can be any other word X. So this X has to be some set of possible words W. So usually with respect to the given antecedent, there will always be at least one particular kind of word which is accessible to that particular kind of antecedent, and this means this word is similar to this one. So now FAWs are those words in which A is already true. It is a subset of those words in which A is true. So this is the first condition which we have. We do not have to impose any condition, whereas in the case of second condition, if W itself is such that, that means this W itself is such that your antecedent is already true there, then any world where the antecedent is true needs to be taken as the accessible word. So in conditional logic, what is of utmost importance is that we need to observe the antecedent and we need to see in which world it is true. If A is true in this actual world itself, that means this world is accessible to itself. So that means we are imposing additional constraint on the accessibility relation, that is what is a reflexive property. So now using this, if any conditional logical system obeys these two rules, it is called as C plus. If it does not require this one, it is only C. If it follows just only this one, it is conditional logical system C. C is not that impressive in a sense that there are many cases where the antecedent is not just true in the possible worlds etc., but it is true in the actual world itself. So in that case you need to extend the C to C plus. So now let us consider some of the semantic tableaux rules for C and C plus, and we will jointly study these two things in somewhat detail. Just observe these two things. So now in C we have only one particular kind of rule. These are like this. So there are alpha and beta rules. These are like this. A implies B is true in a world I. So this is going to be true in a world I when I, R, A, J exists, then only you have this thing. B is true in a world J. It is not telling whether A is true there or not. So A together with ceteris paribus clauses same as the one which you have here, but we are not talking about whether A is true in that world or not explicitly. So this is the first rule, and the second rule is a conditional sentence which is true in a world I. The negation of that one is like this. You have to go to a new world I, R, A, J, and in that world not B is going to be true in the world J. So now just by using these two rules, let us consider some simple examples like modus ponens and modus tollens. First we will work on modus ponens, and then we will see whether it holds in C or not. Modus ponens is considered to be a good validity, whereas whatever we have seen in the case of antecedent strengthening, that should not come as a theorem in our logical system. So now let us consider bad validity first of all, and then we will see the good validity later. A and C implies B, whether this holds in C or not. So now what we are trying to do is we are applying semantic tableaux method on this one, and we are trying to check whether A and C implies B follows from A and B or not. Ideally speaking, it should not follow in our system. So in semantic tableaux method, what you do is you start with the premises and negate the conclusion or the consequent here A and C and B. So now all these things are so now we are in a world 0. Let us assume that you are in a world W0 or W or something like that. So now always when you are using the semantic tableaux method, you should ensure that you take care of the negation part first, and then followed by that the original formula A implies B. Just like in the case of in the modal logic, we have seen that always work on possibility operator and move to a world and then open up this necessity operator. So now, so this needs to be first, what is the antecedent here? A and C is the antecedent. That's why we have written like this. Whatever is the antecedent, it needs to be written here. So now let us assume that we are moving from I to J. So now we need to use this rule I, R, A, J, where the consequent is, negation of the consequent is true there. Now coming back to this one, this is antecedent here is A. So in conditional logic, the one which I'm going to talk about in a while from now, in all the conditional logics, what the most important thing is that the antecedent of your conditional. It makes sense only when you talk about the truth of the conditional with respect to the the antecedent, and with respect to the antecedent permissible words where the consequent is true or not. That is the one which we are trying to talk about. So now this is still in a world I. So if we move from, although we move from J, but here the antecedent words with respect to this one where not B is true is with respect to A and C, but here it is with respect to A only. So now it is with respect to J. So now we will be tempted to, the moment you see literal and negation, we will be tempted to close the branch, but you are not supposed to close the branch. Why? Because A and C words, the words which are related to A and C are different from the words which with respect to A. For example, if you say sugar in the coffee and kerosene in the coffee, that is A and C. These words are totally different from the worlds in which there is only kerosene in the coffee or just sugar in the coffee. A and C worlds are always different from A worlds. So this should not be, there is no way in which you should close the branch. So that's why this branch remains open. So that's why this formula A and C implies B doesn't hold here. So now what about simple formulas like modus ponens? So modus ponens tells us that A implies B whether it leads to B. If you have a conditional A implies B and A is also true, that's why B follows. So now as usual we begin with the negation of the conclusion, so that is B. Now we start constructing semantic tableaux, semantic tree for this one based on these two simple rules, and this is going to be like this. So all these things are true in a world I or J, whatever it is, you take anything into consideration. So now there is no negation of A implies B. So now this A implies B is nothing but I or A J, and in that world J your B has to be true. So now this is going to be an open formula because not B is true in a world I and B is true in a world J. So now if you write it like this, this is RA, and then the open branch will give us the counter example. So now it will be like this thing. There are two worlds, I is related to J with respect to the antecedent of your conditional, and in that world J, B is true, and whereas in I, not B is going to be true there. So this will serve as your counter example. So that means A and A implies B can be true, but B can be false. This shows us the example. So modus ponens doesn't hold, but we don't want modus ponens to not to be a theorem in our logical system. So what needs to be done? In C, nothing is interesting because we are not talking about whether what will happen if the antecedent is true in this world itself. So now this leads us to view the second point, that is, if the world itself is such that your antecedent is already true there, and that world needs to be taken into consideration, that itself will serve as FAW. FAW is any such kind of world which is accessible to the actual world W. So now if that is the case, then W should be treated as FAW, that itself needs to be viewed. That means if a world is such that your antecedent, for example, if you are evaluating a conditional sentence A implies B, if the world is such that A is already true there, and this is the world which will serve as FAW. So now following this reflexive property, we need to change our semantic tableaux rules a little bit, and then we come up with this thing. So we slightly change the rules of this one, and then we talk about the same rules in a different way to incorporate the idea that those worlds in which the antecedent is already true needs to be taken into consideration. So now in this case A implies B is true in a world I with respect to I R A J. A is also true in that world where B is also true. So now we need to write like this: A is true in a world J, wherever A is true, not B is also true there. Also there is one more rule which we need to use, that is like this. So either this is another rule, it happens in this way that either not A is true in a world I, that means A is false in the world I, like in the one which we are talked about this thing. If A is true, this is the one which you need to take into consideration. There are only two cases, either A is false so that you will not take this world into consideration, or if it is true then you have to take this world into consideration. That is, if A is true in the world I, then it has to be I R A I, where of course A is true. If suppose if you are evaluating A implies B, B will also be true there. Wherever the antecedent is true, the consequent also has to be true there. So now taking this into consideration, let us see whether our modus ponens holds in C plus or not. So, we want good validities to be there and all the bad validities to go away. First, let us assume this thing. Let us consider this one: A implies B, B implies C, and A implies C. Whether this holds in C plus or not. So, now you take the negation of A implies C and start constructing the tree using the C plus rules. C plus rules are these. So, now always handle the negation formula first, and this is going to be, you have to go to a new world. Now, first you need to write the antecedent of your conditional. This is accessible to relation with respect to the antecedent. Here the antecedent is A, here the antecedent is B, here of course it is A only. I, R, A, J, then in that world where A is true in a world J, not C is true in a world J. Now this is over. Now B implies C. Now I, R, A, J is already the case. That means in all those worlds in which the antecedent is A is J, then this will become A. In all those worlds where A is equal to J, B also should be true in a world J. So this is over, and then this is the one which we have. So now the antecedent here is B. That means I, R, B, J, and in all those worlds in which B is true in a world J, and C also has to be true. Now there is we have a temptation, we will be tempted to close this C and C here. This not C is true in a world J with respect to RA, I, R, A, J, but this C J results in with respect to I, R, B, J. So these are two different antecedents. There is no way in which you can close the branch here. This branch remains open, and from the open branch you can construct a counter example. So that means this doesn't hold in C plus. Now consider good validity like modus ponens, whether it holds in C plus or not. Let us see. So A implies B, and we have B. So you negate the conclusion. Here it is this thing B. Now start constructing a tree diagram for this one. So now A implies B. A implies B is this thing I, R, A, because antecedent is A, so it is B. Now in that wherever A is true, I, R, A, J. Now in that world wherever A is true in J, B also has to be true in a world J. Now this doesn't end here. If it is C, it ends here only. You cannot cancel Bj and not Bi. This is true in a world I. This B is true in this world and not B is true in any other world. So this cannot be cancelled. Now we need to use this rule. When we use this rule, particularly whenever the antecedent here is A, whenever the antecedent is true in a world I, this world also needs to be taken into consideration. That is the additional property that we have. So now we need to use this rule. Either that A has to be false in that world I, or if it is true in that world I, it has to be I, R, A, I. So now I, R, A, I. So now not A, I is true in a world I, and A is true in a world I, it closes. Now A is true in a world I, here B is true in a world J. B is true in a world J and J. Now this can be viewed in a different sense also. So instead of going to J, you can even go to I itself, I, R, A, I. If that is the case, then it will be like this, A, I and B, I. So the branch closes. So now let us assume that this is the case. Now A is already true in a world J. Once again you can apply this rule, either not A is true in a world J, or if A is true in a world J, it has to be IRA, JRA, J. So now you have not AI which closes. So one second. Actually, this should not come as this should come as validity in our conditional logical system. So that's what we are trying to see. So something went on wrong here. So let me just consider it again. A plus B, A, and then B. So now if you deny this formula B, which is true in a word I, all these things are true in a word formula I. So now A implies B is like this, I R A B, wherever A is true in a world J, B also has to be true in a world J. And these 5 properties are satisfied, then it is called S system. Unfortunately, S does not have any semantic tableaux method as of now, so it can only be discussed in terms of spheres. I will give you 2 examples and then I will end this lecture. So where I will be talking about system of spheres model C1 and C2. So now these are the 2 extensions of further extensions of S. Anything which is valid in S has to be valid is an extension of S in particular. So that is this thing. If there are 2 worlds X and Y, and they are considered to be those worlds in which antecedent is true, FAW, X belongs to FAW and Y also belongs to FAW, then these 2 worlds has to be same. This is the view which is followed by Robert Stalnaker, and this assumption is also called uniqueness assumption. So the idea is very simple. You take any conditional into consideration. I am just giving you the idea of this thing. In C1 it is like this, any conditional A implies B, and with respect to the antecedent of your conditional, there may be many worlds which are accessible to this one, W1, W2, W3, etc. So out of all these worlds, W1, W2, W3, etc., according to Stalnaker, although all these worlds W1, W2, W3 are similar to the antecedent of your conditional, but there is one world amongst all these worlds which is considered to be unique world. So if you say that something is unique, it cannot be 2 worlds that are there. So out of these 3 worlds, there should be only one world which is unique to the actual world. This is what is called as uniqueness assumption. So now let us talk about some examples with respect to system of spheres and C1 and C2. So in system of spheres model, we do not have any clear cut semantics for that. The idea in system of spheres is that any world that you are trying to take into consideration comes with some system of spheres. So this goes on and on like this. So the idea here is that this is considered to be the actual or real world. This is the world that we have, W, and any world W comes up with various system of spheres. There are all the worlds which are closer to W. It could be like you can view it in this sense that observing that you have an onion in your hand, you peel it off and all, ultimately you enter into the center of that onion, and that is considered to be W, and all the layers are considered to be your system of spheres. So that means the worlds that fall under this inner sphere are more similar to W than those worlds in which it falls on this one. So why we need to abstract this and view in this way? Because any given world, any antecedent comes up with many possibilities. All these things can be grouped in the form of spheres, and you have to visualize this in this way, that those worlds which fall under the innermost sphere is this one, they are more closer to this one than, and those worlds in which fall under the next innermost sphere, that is, let us say S1, S2, S3, S4, etc. So now this is like S1 is a subset of S2, subset of S3, etc. Then it goes on, and then ultimately it will become W. So, so now the idea here is that if you want to say that a formula A implies B is true in a world I, what does it mean to say that A implies B is true in a world I with respect to system of spheres I? It is simply like this. First we need to see the antecedent, and with respect to the antecedent, together with that there is a smallest intersection, smallest sphere where A is considered to be true. This is the smallest sphere. In that smallest sphere your A is true. In those worlds your B has to be true. Then obviously the conditional holds, otherwise it does not hold. So now how to talk about these things with respect to some kind of examples like this. So now in this case any world W which comes up with like this S0 W, the innermost sphere, and then the second innermost sphere is this one, and it goes on and on. Ultimately it will become Sn W, and this is equivalent to the set of worlds W. So that is what is the case here. So now let us consider 2 or 3 examples, and with which you will see how to solve some of the problems with respect to this thing. So these examples are like this. Let us assume that let us try to solve this problem. P implies Q and Q implies P, whether this follows or not in S. P implies R if and only if Q implies R. So you have to note that when you have when it does not hold, then you can construct a counter example. So whether it is valid in, you have to show that this is valid in S. So now what do you mean by saying that P implies Q is true? It is nothing but FPW is a subset of those worlds in which your consequent is true, and Q implies P. Q implies P means FQW are those worlds in which P is true. So now by condition 4, if FAW are those worlds in which B is true, FPW are those worlds in which A is true, then this is not the case. FAW is same as FBW. So these 2 worlds have to be the same thing. So this means from condition 4 it follows that FPW is same as FQW. Hence now we come back to the consequent. In all those worlds in which P is true, P implies R means FPW is a subset of those worlds in which R is true. So that is the one you need to write like this. If and only if you write it like this, are those worlds in which FQW are those worlds in which R is the case. So it is indeed the case that it has to happen both sides. FBW is a subset of those worlds in which R is true. If then FQW is subset of those worlds in which R is true, and it should be the other way around also. Since FPW FQW is same, then you can even write it, the converse is also going to be true. That is the reason why this formula is going to be valid in system of spheres model. Yes. So now let us show that this is not the given conditional is not valid in S. So that is this P R Q R which is not valid in this thing P implies R. So now why it is the case that this is not valid in system of spheres model S. The moment you say that it is not valid in S, of course you have to show that your premises are true and the conclusion is false. So now you can have a counter example for this one. This means that PRQ implies R, means F PRQ W are those subsets in which R is true. That is the first one. So this F PRQ W, it has to be at least one word W0, and this W0 is a subset of those words in which R is true. Hence PRQ is true at W0, but you can always have another word FPW. Now we are coming back to the conclusion. So what you need to show is that in all the nearest words where PRQ is true, R is also true, but in those words in which P is true, R has to be false. So now FPW0, it can be any other word W1 which belongs to the set of words capital W, and we can show that it is not, it does not belong to set of words in which R is true. Hence P implies R is false at W0. So that leads us to, this gives us a counter example for this one. So how do we show with respect to system of spheres? So now what we are trying to do is that we are not drawing the system of spheres as such, but it's a two-dimensional picture, so that's why we are drawing squares. So how do we show that a counter example for this one? Or there should be only one word which is unique to the given antecedent of your conditional. And if you invoke this particular kind of property, now coming back to the same example, now in the nearest words where PRQ is true, R is considered to be true, is this word. So anyway, this is false in this one. And the other thing is that in the nearest word where PRQ is true, it can be taken this word also. You can take this word also into consideration. But this does not give you any result here, because the idea here is that if you have true premises, you need to establish the false conclusion. Sometimes it might so happen that you have two situations where your antecedent is going to be true. Then in those cases, if you are using Stalnaker's approach, then you need to take only one word into consideration. So just I will give you one example so that you will understand this thing in a better way. Why Stalnaker wants this uniqueness assumption? So with this I will close the thing, and then rest of the things are considered to be an extension of this thing. You need one thing you need to note here, so that is this one. So if you take 2 is this thing, any word is such that your antecedent is already true, then that word needs to be taken into consideration as your FAW. And this 2 together with this 6 leads to 7, but 7 does not lead to 6 plus 2. So that makes C1 distinct from C2. So David Lewis drops this assumption of uniqueness assumption, and then he talks about this view, a different view, that you do not require this uniqueness assumption. It is uniqueness assumption cannot be established in some of the conditionals. Let us talk about one particular example where it holds in Lewis, it does not hold in Lewis, but it holds in Stalnaker's approach. So that is this one, A implies B, or it is not the case that A implies B. So usually Stalnaker in general he assumes that the negation of the conditional A implies B is same as, by definition it is same as A implies negation B. So now Stalnaker wants to preserve this particular kind of, this is also called as conditional excluded middle, conditional excluded middle. So when you say that P or not P, it is considered to be law of excluded middle, but it happens with respect to the conditionals, so that is why it is conditional excluded middle. So now if you negate this formula and construct a counter example for this one, it is going to be like this, not of so now this is going to be A implies not B. So now this is not of A implies B, and because negation of disjunction is conjunction, so it is going to be A implies not B. So these are all true in a word I. Now if you use C plus rules, semantic typology rules, it is going to be like this. In all those words, it is antecedent is A only in both the things, I, R, A, J, and in that word J, whenever A is true in a word J, not B has to be true in a word J. Now once again, if you use this one, it is like I, R, A, J, another set of rules where A is true in a word J, again it is with respect to the same antecedent, not B, that is B is true in a word J. Now from this you can construct a counter example, and then I will talk about the difference between David-Lewis approach and the Stalnaker's approach. In Stalnaker's approach, he takes this as validity in his logical system, whereas David-Lewis considers that it is not going to be valid. There are some justifications which are given. Of course, I am not going into the details of it, but so now here is a counter example for this one for David-Lewis. It is like this. So there are two worlds which are possible here. In one world, A and not B is true, and in another world, A, B is true. Now coming back to this example, A implies B, or A implies B, or A implies not B. Now there are two worlds in which the antecedent is true, but for Stalnaker, either you have to take this into consideration, only this world, or this world into consideration, but you are not supposed to take both the worlds into consideration. So what makes this conditional false in David-Lewis approach is that this thing, in the nearest worlds where A is true, B is false, so that makes this thing false, the first conditional false. Now in the nearest worlds where A is true, again I will take, instead of this one I will take this one, then this also becomes false. So in the process the whole conditional is going to be false for David-Lewis. For Stalnaker, since he follows the uniqueness assumption, especially when there are 2 or 3 worlds which are out there in which the antecedent is true there, you have to take only one world, and that world has to be unique world. Either you fix this world into consideration as unique world, or this one as your another world. It is with respect to this world you are evaluating the formula. So in this way there are differences between Stalnaker and Lewis. Lewis does not require this uniqueness assumption, so he comes up with a different kind of semantics in which he drops this. It is considered to be an extension of S only, but the only one rule which is extra, that is the 7th rule. So with this we will end this lecture on conditional logics. It is conditionals needs to be studied in greater detail. This is no way an exhaustive kind of study on the conditional logics. I just showed you on a tip of iceberg. So we have just begun with the view that whenever you are analyzing a conditional sentence, you need to ensure that you have to take care of ceteris paribus clauses. That means whenever you are evaluating A implies B, you need to understand that it is A plus C and A together with that leads to the consequent B. So conditionals are not straightforward and easy to analyze, although we have the best approach that is available to us seems to be either C1 or C2, but still C1 and C2 has its own problems, particularly when there are some conditionals with disjunctive antecedent and conjunctions etc. as the antecedents in your conditional. So to conclude in this course, we have in this short course I have just began with the crash course on classical logic, because that is going to be the starting point for this course, and then I showed some kind of limitations with respect to the classical logic, particularly when it comes to modal sentences. Classical logic fails to make any such kind of distinction because in classical logic possibility of P, necessity of P and P same. So in the process we will miss out some useful inferences, and in that context we extended our classical logic with the modal logics with two operators, necessity and possibility, and these are called elliptic modalities. And then we just spoke about syntax and semantics of it, and then we highlighted on the relational structures, which are also called some kind of directed graphs or Kripke structures. Then we understood that till 1960s logicians, modal logicians were trying to only prove theorems within various kinds of axiomatic systems. Then it is due to Kripke semantics things have become more simplified, but again there seems to be, as I said in the history of modal logic lecture, I said that there was a lot of emphasis on the relational structures. These possible worlds again are not straightforward or easy to follow. Some view it as maximally consistent set of sentences which are considered to be true, but the problem remains the same thing, that is how do we particularly when you are analyzing conditional sentences, how do we attain the similarity between the possible worlds. It's only an intuitive kind of notion as of now, but still David Lewis approach is considered to be the best possible approach, especially when it comes to the analysis of specific kind of conditional sentences like counterfactuals. So we also spoke about in the last part of this course, in the 4th week, we discussed about one application of modal logic, so that is the analysis of conditional logic. In conditional logic, what you need to note is that you should fix the antecedent first. Antecedent is considered to be the most important thing. So with respect to the antecedent, we are looking for some possible worlds with respect to the antecedent, where with respect to which possible worlds your antecedent is going to be true. In all the antecedent permissible worlds, you need to check whether the consequent is true or not, and in that context we spoke about different conditional logical systems. To begin with, the minimal conditional logic C, we extended with by imposing some constraints on the accessibility relation. We talked about C+, and then we moved on to S. It has only it doesn't have any fixed kind of procedures like in the case of C and C+. Only with intuitive kind of diagrams you can establish the invalidity of a given conditional, but checking the validity is again based on the 5 rules. So this is what it went on. It's only a tip of iceberg, and in the advanced courses you will be introduced with modal predicate logic, and there is another dimension which I have completely ignored, so that is algebraic interpretation, etc. When the strict implication was introduced, I mean we have taken only one direction, that is the analysis of modal operators, but there was another direction which is towards the analysis of conditional sentences or some kind of relevant logics, and there is another direction which leads to many valued logic. So how to interpret future contingent sentences, that is what I have discussed in one of the one of the lectures in particular, when I was talking about the history of modal logic. So that's all we have in this course, and I hope you enjoyed these lectures, and definitely we will come back again with any other advanced course. Thanks.